Hello, today I will be presenting our paper that is at EMNLP 2024, Immunization Against Harmful Fine-Tuning Attacks. So what are we studying? We've noticed that safety guards preventing misinformation, hate speech, toxicity, and stereotype generation in LLMs can be easily circumvented by fine-tuning them in as little as 10 samples. Not only this, but there are several models uploaded on Hugging Face where users are doing this intentionally. Our research question is, under what conditions can we say a model prevents safety guard circumvention through fine-tuning? Because if safety guards can easily be circumvented after model release, can we really claim that these models are safe? The threat model we're working with is one where the attacker wants to use an LLM to do a task that's designated as harmful by the defender. With safety guards, the model would normally refuse to do these attacks. We're only studying a threat model where the attacker is using supervised fine-tuning with a limited budget of training steps T in order to attack the model. We define harmful fine-tuning as simply minimizing the expected loss of a language modeling loss over some harmful data set. When the attacker is successful, they have some proxy function like rating whether or not the samples generated are harmful that is above some harmfulness proxy measure. But how do we defend against these harmful attacks? We're going to present a set of immunization conditions on this emerging threat model of harmful fine-tuning attacks, where we perform some procedure, and then when the attacker tries to do fine-tuning, it fails. The first condition is resistance. Ideally, we want strong resistance, such that if an attacker takes any training steps, the harmfulness will always stay below some designated threshold by the defender. But that might be unrealistic, so we propose weak resistance, where the defender is searching for a model that defends against the harmful fine-tuning attack by preventing the harmfulness from getting above a certain threshold by searching for the maximum number of training steps that the defense can prevent against. Another condition is stability, where after performing these defenses, using some general capability measure like fluency, the fluency should not be degraded. Generalization is especially important for preventing against these attacks because the defender almost certainly will not have the same samples as the attacker. This means that we need to be sure that as the attack samples shift, the defense still applies. This is especially important for cross-domain generalization, where there might be a significant distribution shift, or an adaptive attack, where the defender still wants to demonstrate that this attack drawn from samples that are a significant shift from ones that are defended against will still be defended against. Finally, we have a condition of trainability, which states that our model should continue to be trainable on harmless tasks. We evaluated a simple defense of adversarial loss and showed that that adversarial loss was able to defend in this small demonstration of 75 training steps against a harmful fine-tuning attack, where the blue line is the harmful fine-tuning attack and the orange line is the harmful fine-tuning attack performed on the model defended by adversarial loss. What we see is that after we perform the adversarial loss, as we take training steps on our harmful fine-tuning objective, the model goes from refusing to slowly degenerating and becoming a disfluent model. Thank you for your time and attention.